us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Before we proceed, I'd like to kindly request our members to subscribe and also engage us in the comment section. Now, also check our description boxes for various links of other similar discussions that we're going to have on the concept of thermochemistry. Now, I'd also like to encourage our members to be checking on various other videos, which basically are topics under discussion from mathematics, physics, chemistry, and biology topics. So in today's discussion, we're going to look at the concept of molar heat capacity at constant volume. And of course, we're going to look at this from the perspective of partition function, the rotational partition function of a diatomic molecule. Now, in this case, from our previous discussion, I had mentioned that basically different from the statistical mechanics of an atom, the diatomic molecule can be represented using a rotational partition function, which of course is going to be taking note of the 3 degrees of freedom. And of course, I mentioned that basically for rotation, we have only 2 degrees of freedom in that specific respect. Now, in that particular discussion, we had to consider the concept of a rigid rotor, whereby I had given a heteronuclear atomic molecule for that specific example. And I've mentioned basically that for us to describe the properties of this specific molecule in terms of rotation partition function, we considered the concept of the moment of inertia and the distance from the center of mass. Now, Schrodinger's equation assisted us to solve this specific aspect of rotation partition function, whereby we came up with an overall equation representing this specific partition function, and that equation was in form of the Q R. It is represented as temperature over the rotational temperature given in terms of this theta R. And theta R, as we said, basically is an aspect of rotation temperature which is going to assist us differentiate molecules which are going to display the quantum and the classical behavior in that specific case. Now, the given specific conditions which are going, of course, to give a classical behavior and a quantized behavior in that specific respect. Now, I'm not going to go into details of that specific discussion, but I'd like to encourage us to check our description box for that specific link so that we can have a look at that particular discussion. So this specific, what we refer to as rotational temperature, is given in terms of the square of Planck's constant over 8 pi. This is at the moment of inertia, and then we have this particular Boltzmann's constant given as such. So basically, this represented this particular aspect of this rotational translation or a rotational partition function. And of course, from this rotational partition function, therefore, we're going to have a particular description whereby we're going to use this one in describing the molar heat capacity at constant volume. Now, there's a relationship which I had given in my previous discussion, representing the partition function for a system of n independent molecules at a particular temperature. Now, this was in form of an equation which we had given in terms of Q, whereby we said that for a system of n independent molecules at a particularly for large temperatures, we're going to consider the equation of the form QR, which is a rotation partition function. But we're also going to take into consideration this specific number of independent variables given in terms of n, or independent molecules given in terms of n. Now, this basically is equivalent to what we refer to as T all over this specific. I'm going to give an elaboration of this specific notation, which we have basically discussed in one of our videos. So we're going to have this specific representation given as such. And of course, this specific representation is going to basically represent what we refer to as a symmetry number. And this basically from the concept of symmetry and rotation. I'm going to basically just give a summary on this. So this is going to represent a symmetry number, and this number is going to be used for correcting the aspect of rotation partition functions for reduced numbers of accessible rotational states. And of course, this is going to imply basically then therefore that we have this translation or rotation function given in terms of this specific value, whereby we had 8 pi squared. We just give it in terms of a full representation so that we can just see how that one is going to be applicable. So basically this one is given in terms of, so this basically refers to the rotational number, and this particular rotational number is going to be given in terms of this specific symbol. Now they explained that we have fermions and bosons, which basically have got different description for spins, and for molecules which are going to have a rotational symmetry, then therefore they are going to have a reduced number of allowed levels. And of course, this is going to be, of course, an aspect that is going to appear during the description of a nuclear spin. So we're going to have this specific aspect of the symmetry number, which is going to be a specific factor, of course, which is going to be applied in this specific sense for rotational partition function, and of course, which is going to be appearing in this specific numerator, and of course, it's going to be acting as a factor that is going to correct this specific aspect of accessible rotational states. Now we're going to discuss this one in a different video, but of course I'd like just to give a note for this appearance of this specific notation. So therefore in this particular case, then therefore we have seen that we can represent this a set of quantum rotation or the rotation partition function in this specific form. Or if we consider a case whereby we're going to have a system of n independent variables, then it's going to appear in this specific format whereby we're going to have it, of course, given in this particular formula, which includes this symmetry number which I've given above. Therefore, from this particular description, we're going to see that for us to have the internal energy due to rotation of this specific, of course, kind of arrangement, we're going to have this internal energy given in terms of UR. So the basic description that we have been given for this kind of energy, which is going to be the square of T. And then we're going to have the partial derivative with respect to temperature of the natural log of 1. So this specific number, then therefore we're going to do a substitution for Q. In this case, we're going to have Q being represented in terms of this symmetry number that I've given, which is going to be T all over the symmetry number, and then we're going to have given in that particular case, and this one is raised to power n. So this specific factor has changed, and this is going to be just the normal representation for particularly internal energy, and then we're going to do a substitution for this specific section of the partial derivative of natural log of Q over T, and Q, of course, in this case is going to represent this specific derivative that encompasses this aspect of the symmetry number. I've said that the symmetry number is going to cater for a specific case for the spins, and I've said we are going to discuss that one in a different video. Now this specific formula then therefore is going to reduce into a form whereby we're going to have it represented as nk bt, whereby we're going to have the partial derivative with respect to temperature of the natural log over T all over this specific symmetry number, and then the rotational temperature given as such. Now in this case, we have used the property of a natural, of course, exponent, the natural logarithms of this specific case, whereby this particular aspect of n, which is an exponent, is going to appear as a coefficient, and then we're going to have this specific section, and the rest of that one is going to reduce into that one in terms of loss of logarithm. Now if we try to look at that particular end, then therefore we are going to consider this specific equation that we have given at the last part of the discussion. Now we're going to consider this aspect of this particular equation, which is going to be a derivative with respect to temperature. Therefore, this is going to give us a version of the equation given in terms of UR, which is going to be given as nkbt square of that. And then we're going to have the derivative of this temperature, of course, with respect to the derivative of this natural log of T with respect to temperature. And basically, we have said that this can be given in terms of nkbt squared, and then we're going to have 1 over T given as, of course, the value for that specific derivative. Now, we're going to have this one still reduced to nkbt, and of course, which is going to be the rotational internal energy given in that specific case. Now we have said that basically if we are going to have the molar heat capacity at constant volume, then we can use the specific description that we have had in terms of the concept of Boltzmann's constant and the universal Oscar's constant, whereby I'm saying that the relationship between the two is that R is equivalent to NA KB. Therefore, if we consider this specific aspect of the equation which we have come up with, it's going to represent this specific aspect, and therefore UR is going to, of course, reduce to RT. So therefore, if we consider the molar heat capacity at constant volume, we're going, of course, to have a derivative of this specific the internal energy, which is a rotational aspect, being differentiated with respect to temperature, and therefore our molar heat capacity, which is C, of course. So this is going to be CV, which is molar heat capacity at constant volume, and then therefore this is going to be a rotational aspect which we have said, and therefore it's going to be represented as a partial derivative with respect to temperature stat of this specific U are given in that particular case. And we're going to do a substitution for this one and have the molar heat capacity at constant volume of this rotational partition function given in terms of the partial derivatives of RT. Now, if we do this specific evaluation, then therefore it's going to reduce into a number of R, which is of course the universal constant given in terms of that. And this is going to be the molar heat capacity at constant volume for this rotational partition function, of course. And this is going to be a property of a rigid rotor, which we had considered in our initial case. And of course, I assume that we are going to be taking note of that as we come across problems related to this specific case. Now, that is it for today. Kindly check our description boxes for various other videos which are related to this, and subscribe to our channel for more. So that is it for now, guys. Bye. God bless you. Catch us in our next video.